Hi, this is Colton Suter and Kyle Gardner, and we chose to do our heat transfer project on defrosting your windshield.
Yeah, so here's your typical Rexburg winter morning, and just want to see how long it would take to defrost your windshield, and we want to see if we could calculate that using what we have learned in our heat transfer class.
So one suggestion that Brother Danes had was to look at this theoretical study that's been published in our heat transfer textbook, which is called Impinging Jets. So the idea behind it is that using some measurements and other things, including Reynolds number and all of that, we can calculate a Nusselt number, Nusselt correlation, that we can then use like we have previously. We can use that to calculate our H value and in turn calculate the heat transfer that this impinging jet is causing. And so this impinging jet, some things that need to be known about it are that it's assumed to be perpendicular to the plate, and we'll talk about some assumptions that we've made later on in this presentation. But yeah, basically use the parameters that are shown in this picture, and we were able to take measurements of the width and those kinds of things so that we could find out whether or not the correlation would work for our project and the corresponding Nusselt values and heat transfer coefficient.
So this slide just shows the Nusselt correlations for impinging jets and how they're related to the Reynolds number and Prandtl number of the jet. Also another parameter shown is the AR naught, which just has to do with the spacing of the nozzles and the size of the nozzles. And then on the right are just some parameters that our numbers need to fall in for these assumptions to be accurate to model this case.
The beginning of the experiment was pretty simple. We basically relied on a frosty winter morning, which didn't happen too much, so our experimental data didn't accumulate too many numbers, but we were able to get some good experiments in. And so after starting the vehicle, we would let it run for several minutes without the defrost on, and we would scrape a patch off on the outside so that we could use some thermocouple tape and tape the thermocouple on the outside so we can take the temperature of the surface of the glass. And we would also take a thermocouple and do the outside temperature and the inside temperature of the vehicle, and then we would use one to measure the temperature of the air also. And so as you can see in this bottom picture, we are trying to melt a 5-inch wide strip similar to what the picture shows, and we timed it, and we also timed to when the temperature gets to 0 on the outside, because that is when we are dealing with the latent heat of fusion, and that is a calculation we also performed later on.
These are all of our results. So given the airspeed coming out of our heater, we got a Reynolds number of 11,706, Nusselt correlation of 28, and an H value of 59, which matches up with the table in our book for H values for forced convection and gas. And using those values, we were able to calculate a Q from our heater of 297 watts. And like Colton mentioned earlier, we let the car warm up first. That way we could get a hopefully constant Q just to make our calculations a little bit simpler. And then the time for the outside of the windshield to reach 0 degrees Celsius was 39 seconds using the one-term solution. And we also thought we'd just try calculating it for lumped capacitance as well, got 175 seconds. And using the latent heat of fusion and the mass of the frost that's melted on the 5-inch strip of the windshield, we calculated a time to melt of 6.8 seconds. As you can see, our experimental results, the time to reach 0 degrees was pretty good. 20% error is not bad, especially considering all these correlations are going to be within a certain percent off anyways. However, the time to defrost a 5-inch strip was not so good according to our experimental results with an 87% error. And then the lumped capacitance assumption gave us a percent error of 257%, so that is clearly not the correct model for this case. And then again, one of the assumptions we made in this is that even though the impinging jets are not normal to the surface of the windshield, that it would still be close enough to get accurate results.
Like Kyle said, one of the assumptions we made was that the impinging jet would be normal to the windshield, which it wasn't, obviously, and that can accommodate for the difference in time, that 20% difference. And we neglected radiation due to the small difference in temperature on the outside, and we also neglected convection on the outside because we did take those temperatures and we did calculate those values, but they were negligible compared to the heat transfer from the convection on the inside. Another assumption was that we assumed the frost was about 5 sheets of paper thick. Some of the mornings that we did this on, there was some fairly thick frost on, so we thought that was a good assumption, 0.5 millimeters. And so 2 of the parameters that needed to be met for the impinging jet correlation were not met with our size measurements, mainly on the width of the air vents and a couple other things that combined to make it so that 2 of our parameters were slightly outside. They weren't drastically outside, but they were slightly out. Again, it's gonna make a difference in the outcome.
And for our conclusion, basically for this, one-term solution was definitely the way to go with only 20% error. And some of our results might have been skewed just by incorrect assumptions, like Colton mentioned with the sizing of the vents. With my particular car, just some of those parameters weren't quite right, but if you use a different car, they might have lined up perfectly and given better results. So that is our presentation on defrosting the windshield.
And here is the book. You can find this in the textbook on impinging jets if you're interested. Page 400 and something. You can look it up in the back.